different electrodes to be the ones. Have I got it correctly attached? The negative is attached to the zinc. Yeah. Okay, can't argue with that. Now, what do you think will happen if we use, say, a rusty screw? Should we try that instead of the zinc? Okay, so let's put a rusty screw in somewhere. See, it says no volts. I take it the screw is iron. Look at that. It is correct. The rusty screw, I should have red and white wire, so I don't have to. Okay. See the voltage? Higher or lower? 0.37. And so let's make a note of our data. So attached to the negative is the iron. Iron, still copper, 0.37. Okay, let's try, I think this is tin. Anyway, it's solder. Let's stick the solder in. Solder is normally tin, but sometimes it's got a bit of lead. I doubt this is lead. Okay, it says naught. Let's attach it. Let's presume it's tin. What does it say? 0.43 with the tin. That's to the negative and the copper is still the positive. And I think I just want to check nickel, and if I can find lead. Let's just try nickel, which is this coin. So nickel, I just want to find the little holder I made for the zinc. Where is it? Otherwise I'll just make another hole. Okay, so this is nickel, and it's 0.17 volts. 0.17. Now we've got to think, which electrode is going to be your positive one and which your negative one? I mean, what is happening at the negative electrode and what's happening at the positive electrode? I'll hint, oxidation. But which one has been oxidized? Which one is giving off electrons and which one is gaining electrons? So if you have a battery and you attach something to the negative electrode, okay, let's put it this way. Your voltmeter, which do you attach to the negative side of your voltmeter? The positive or the negative? With your voltmeter, you normally attach your red wire to the positive of the battery and the red side of your voltmeter. So this is a voltmeter. The red side of my voltmeter must be attached to the red side or positive. So this must be my positive. It just seems so wrong. And this must be my negative. This one is positive because it's lost its electrons to this one. So here's what's happening. It just seems wrong to my experience. Copper has lost its electrons to the iron, The iron is now negative, the copper is positive. Happy with that explanation? Does it make logical sense? Does it make logical sense? One metal's been oxidized, one is being reduced. The one that loses electrons must become positive, and therefore it's attached to the positive side of our voltmeter. One electrode gains electrons from the other metal and becomes negative. That's attached to the negative side of our voltmeter. So it seems like if we were to classify these in order of which electrode gives electrons the least easy and the most easy, which seems to be the order in which it gives electrons the most and the least. Just try and think that through. If it gives the most, it will have the highest voltage. Which of these has got the lowest voltage? This one. So nickel gives, copper gives nickel electrons the least. So this must be the least reduced. Least reduced. Lowest. And which one oxidizes the most here? Look at this, 9. Look, your copper gives to the zinc with the most voltage. So these two really, this one wants to give, this one wants to get. Does that make sense? Different metals want to give electrons with different amounts. And different metals want to gain them electrons with different amounts. And so you see, if you start connecting different metals to copper, this one gains electrons a lot, this one gains it second most, this one gains it third most, this one gains it least. So copper, it hasn't changed, that's our constant, but zinc will gain or be reduced most easily and least easily nickel. So what that does is you then end up with a table, a redox table. How many of you seen this in exams, a redox table? You've seen this table come up before. Okay, everyone happy with it? Seen it? I meant to have, you'll find it in one of your textbooks, maybe you'll find it somewhere in that study guide. We're going to focus on this table now the most for a while. Kaylee, what page is it? It looks like it's right near the back.
Page 239.
239 on your 249 in your workbook. $249. Now guys, you'll see there's two equivalent tables. Look for the table on page, I want the table that has lithium at the top. So it's 248, 249, 250. It doesn't number the pages, 250. Look for the table with lithium at the top. Never, ever use the table with fluorine at the top, because I'm going to teach you with lithium at the top. Why they still give out two tables in the 2020s, I have no clue. It's just a waste of paper. It's the same table, just in reverse order. So why do it? All happy? Okay. Now, what does this table tell you? First of all, if you look at it, all the metals are on top. For example, lithium, potassium, calcium, barium, Sr, strontium, calcium, sodium, magnesium, etc. They're all metals at the top. Now look at the bottom. Fluorine, cobalt, I think it is. I should get my glasses. Whatever they are, but they're all non-metals at the bottom. Okay. Do you see voltages on the side here? Do you see those voltages on the side? That tells you how much or how little it wants to be oxidized. That's the voltage that it's like our lemon experiment, exactly like we've done it. And just as you get voltages, so they don't use a lemon, they use a slightly better technique, which I will show you. And then they come up with these voltages. So now they arrange the elements from the most metallic to the least non-metallic, to the most non-metallic at the bottom. And in between there, we don't know what we are. Are we a metal or are we a non-metal? We don't know, we haven't yet decided. Okay. I'm really going to give you the chemistry 101 here. Okay, metals, do they like to give off electrons or not? Yeah. Metals, do they like to give off electrons? Yeah. Yes, they're generous, they give electrons. What are electron symbol? Let's call it E-bucks. Metals are just E-bucks, they're big spenders of E-bucks, they give off electrons easily. For that reason, and please don't take offense at this, I always think of metal as men. They're the ones with up with the wallet, let's pay for the supper, let's pay for the marriage, let's pay for the everything. As I said, please don't take offense, this is 2020, I know it's changed, thank goodness it's changed. But baby boomers, this is how we grew up. Okay, have you got it fixed in your mind though? Although it's just an analogy, the metals are the ones that give out the electrons. Now, you get very givey men, and you get somewhat stingy men. You get some very givey metals, and you get some not so givey metals. So this is the order we've arranged them in. The most generous metals, the ones that oxidize the easiest, which is who? Who's on the very top? Lithium. I always think of Liam, like Liam Neeson. He's the most giving man in the world. Does the analogy hold? You getting the analogy? You can reject the analogy, it's just a way of remembering it. Don't blame me, it's just an analogy, folks. I don't subscribe to this. Men should not give, they should not open doors for women, they should have doors open for them. Okay, or whatever you feel. I don't subscribe to that either, but anyway. Okay, no commentary on society. So lithium is the most attractive man in the world. Why? Because if you go to supper with Liam or lithium, who's going to pay? Are you going to pay? No. Liam is going to pay.
Is the Neeson himself?
Because he's the most giving person in the world. Okay, just have a look at potassium and calcium underneath. If potassium and calcium go to dinner, it goes L-I-K-C-A. If potassium and calcium go to dinner, who's going to pay for it? Who's going to be giving out electrons?
Potassium.
Potassium, because he's second most giving. Does that make sense so far? Does that make sense? Okay, let's continue then. Now in this terrible analogy, we have the non-men at the bottom, otherwise known as the woman. And women were there to get. They're there to be paid for, they're there to look after, everything you pay. The men pay, the women get. Now, the most attractive women are the ones who get the most because they can. So who is the most attractive woman on this table? Who's the most getty kind of woman? Blurring. Again, this is an analogy, don't blame me. So, if Liam and I think of fluorine as Megan Fox, F for Fox. Okay, Megan Fox. Find me another woman with an F and I'll call her whatever. So if Liam and Fox go to dinner, who's going to pay?
Mr. Neeson.
Liam's going to transfer money to Megan.
Ja, trouwens wel goed.
Now, if Megan and bromine, which is halfway from up, a quarter way up. Now, bromine is also non-metal, so bromine is also a woman. If Megan and bromine go for a dinner, think about it. Who's going to pay?
No one.
Who's going to pay?
Bromine.
Bromine's going to be oxidized. Fox is going to be reduced. Always. So what are you going to do in the exam? They're going to ask you a question. They're going to give you two metals, like zinc and copper. You're going to go to this table. You're going to look for zinc and copper. The one on the top is going to be oxidized. The one on the bottom is going to receive the electrons or be reduced. That's as simple as it is. Now let's suppose you forgot what I said and you went to the wrong table. The one with F on the top, you're going to get it totally wrong because now it's reversed. The top ones are the ones that are going to be reduced, and the bottom ones are going to be oxidized. So you're not going to make a mistake. You're going to go to your table and you're going to find zinc and copper. And you're going to find the one on top is the one that's always going to be oxidized, and the one at the bottom is the one that's going to be reduced. Then what you're going to do is you're going to go to the voltage next to it of both voltages, and you're going to, from those voltages, you're going to change one of them around and add the voltages. Look, there's multiple ways you're going to do this. I'm giving you the old-fashioned way just because I remember it, but then I'll give you the proper way. You find the biggest voltage, whether it's positive or negative. You make the biggest voltage positive, but one of them has got to change. Because all of these are written with the electrons on the left, on the right. They're written as if they're all written with electrons on the left, as if they're gaining electrons. But if you have oxidation, you must have reduction. So one of them has got to reverse. So just the old way we teach it, look for the one with the biggest voltage, irrespective of sign, make sure it's positive, and if you have to turn it around and change its sign, then you do that. Otherwise, you change the other one around. But I'll give you a formula that does that better. And then you're going to know what's the voltage of your battery. Okay. Now, in the exam, we don't use lemons. So, let's make ourselves a proper what kind of cell is this?
Voltaic.
A voltaic or
Galvanic.
galvanic cell. So we take how many beakers? Two. Into the one we put copper sulfate. Into the one with the copper sulfate we put copper metal. Everyone happy with that?
Yes.
You put copper nitrate, copper anything, but something with copper in it and the metal. Sorry? No, that's the soft. Is that tin? Well done. Where is our piece of copper? Where's the copper gone? Oh yeah, there's some copper, but got to be somewhere around here.
So I think it was all been done in the school. So.
Okay, so there's a piece of copper. Put it in there. Thanks for telling me. Now, let's get a piece of zinc. So there's our copper with copper metal. There's our zinc. This is actually quite a brittle metal. It's almost broken. I see. Okay, so there's our zinc.
So you have to put it down.
Because
Zinc.
it's very active.
And I take some zinc sulfate. Zinc sulfate. The same as copper sulfate. I hope it dissolves. You always have to get something that dissolves. So there we got a solution of zinc and zinc metal. Now we're going to create an equilibrium with the zinc and its ion. Zinc plus plus ion. So it's got to dissolve, otherwise it's not aqueous. In the exam, always, if they don't tell you what, always choose a nitrate. Like zinc nitrate, all nitrates dissolve. Sulfates are pretty good at dissolving. Okay, so there it's dissolved very nicely, thank you. So now we got two solutions with zinc and copper. Now you need a salt bridge between the two. How do you make a salt bridge? You get some salt, sodium chloride, ordinary table salt. Okay?
So you can't, so, no, you can't see the action.
Can't you see it?
No, then, this
Yeah, you can't see
So
those.
just put the phone here on Aiden's table.
Okay, we might do it. So here is a brine or table salt solution. We know table salt dissolves. Doesn't matter. Actually, our salt bridge, you can use anything, any iron substance that dissolves. Fill it up. Fill her up, sir. Now, we need a little piece of cloth to stuff on the ends. Anything porous. So, we stuff that cloth into the end there. We're going to have to stuff another cloth into the other end. So let's just fill that. It's going to be quite hard to do without getting air bubbles in it. So let's just get ready with another piece of cloth.